Let's start. This is Samarth, and today we'll be discussing differentiation and also some parts of it, or like what kind of differentiation we'll be studying, second order differentiation, and the trigonometric part of it that we skipped the last class, right? So we'll try to continue doing that. Yes, so starting with differentiation, as we know what a differentiation looks like. So the rate of change of quantity y with respect to another quantity x is called the derivative or differentiation coefficient of y with respect to x. So in simpler words, dy del y by del x is is what a derivative is. Okay. So this is the basic part of it that we did yesterday. So now continuing. So we know what first principle looks like, right? So we did limits the other day. So if we are defining the differentiation from first principle, that is f dash of x would look is equal to dy dx of fx. And that can be defined as limit when del of x is going to 0 over the function f of x plus del x minus f of x upon del x. So some standard differentiation formula that you can learn. These are really important because these have various applications in differentiation and the topics that we are going to study in the future. And these are also very basic. If you're preparing for JEE or you're studying in class 12 and almost done with the syllabus, then you will find that these equations are very basic and you might already will be aware of these. So yeah, again, this formula differentiation of sign, we can see what does differentiation. So we can just sometimes we can also intuit differentiation. So see, this is the sine curve, right? Yeah, so I'm not able to draw the sine curve. So this is the okay. This is the sine curve, a rough draft of it. So if you check out the slope here, the slope here at the sine curve is 1. Here it is 0. Here it is -1. So this is more than equal to a cos graph. So trigonometric functions and their derivatives are usually a part or a subpart of their subpart of a trigonometric function. So for sine, we have it as cos. For cos, we have it as minus sine. Then for tan, then for tan, we have as x square x, where x is not equal to this. Then for cot, we have minus cos x square. For sec, we have sec tan. For cosec, we have minus cosec cot. These are something that you can learn. Then we also have the formula for inverse trigonometric functions that you can learn. Of course, by learn, what I mean by learning these formulas, the best thing you can do here is you don't have to mug up these formulas. Like, of course, first thing that goes for mathematics is that you have to practice, right? So while practicing, you will notice that if you practice to a very large extent, so if you practice to a large extent, you will remember the formulas by yourself. You won't have to like see and mark these up. So I would suggest you that practice to a large extent, and these formula would like come handy to you later on. So yes, moving on. So these are the formulas that we have. This formula, this. This is again a formula that we have. This is again a formula. I'll get back to you what do we mean by this. This is another representation of an inverse function like sin hx and cos hx. So what do we mean by that? We'll get back to this later on because this has not been studied to a very large extent. So we'll come to that later on in the class. So yeah, if we check up the formulas once, so what is being said here? The derivative of sine inverse x is equals to 1 by root of 1 minus x square. Okay. So we can like check this out by taking sine x. So sine inverse sine x would give me x, then 1 upon root of 1 square. So 1 minus x square is sine square x, that would be equal to cos square x. So root of cos square x is equals to cos x. And then 1 by cos x would be sec x. So this is what we are getting, right? So, and dy by dx would also change here. So we can prove this formula very easily by substituting x as sin x, cos x, cot x, or any trigonometric function that suits the condition at that time. Okay, so let's move on. So C differentiation. So d by dx of c of fx. Then so c is a constant, so it would go out of the differentiation, and we are simply left with d by dfs dx of fx. Okay, then this formula we have. This is the plus and difference rule. This is the product rule, and we can generalize the product rule as well. So general, what is the general form of the product rule? You can see here. It is a very important rule that you can learn about. This is the differentiation rule or the quotient rule, sorry. Yes, moving to the next part of it. So it is given that d of dx by fx is equals to fx, then d. Okay, so this is the identity that you can learn. So what is this identity stating? Let me write it down. Just turn it. The identity is saying d by dx of fx is equal to fx. It is given. Then what is implied? D by dx of f of ax plus b is equals to a. Okay, so this is the identity that you can learn. This might have some application on your questions in the future. Now, differentiation of a constant function is zero, of course. Why is it zero? If we want to see, a constant function would look like this, and the slope of this function is always zero, right? So that is why the derivative of a constant function is always zero. Again, as I use the geometric form of the derivative on the point, so what we get is the derivative of a point simply means that the slope of the tangent to the curve at that point. For example, we have this curve and we have to find the derivative here. So what we do is we find the slope of the tangent here, and this whatever the slope of the tangent might be, you will get the same value of the derivative, right? So this is a geometric form of derivative that we might have known earlier as well. So talking about different types of differentiable functions. So differentiation of composite functions chain rule. Okay, so chain rule is something that we did in the last class as well. So I think we can move on with that. So yes, differentiation using substitution is something that we have to discuss in this class particularly. Example, in the first, if we have a function of root of a minus x square. So this seems a bit tricky to solve, right? One would say ki we can take a square minus x square is equals to t and then we can solve it apart. We can do that as well, but our life gets much more easier if we take x is equals to a sine x or cos x, right? If we take these values, our differentiation becomes much more easier. What are we left with? A cos x differentiation that can be easily done, right? Or theta in this case. Similarly, if we have a root over plus sign, then we use tan or cot. If we have minus sign, then we use sec and cosec. Again, these are something that will come to you when you memorize it and solve some questions. So we'll end up using these theorems and you will get to know of their applications. So differentiation of implicit functions. By implicit, what we mean, we had discussed this earlier also. Implicit is when the function is not, when it is not clearly defined that what is the independent variable, what is the dependent variable. So can also be the independent variable or variable, so it is not defined, right? So, so sometimes we have to create with respect to x as well, and getting dy by dx. This is something that we have to do, and we can just simply do that because we are aware, right? Dy by dx is equals to dx by dy. Sorry, 1 upon dx by dy. This we had done in the last class, right? So this is something important and we can use in our equations as well. Okay, so now moving on, what we have is differentiation of parametric functions. Okay, so this is also very interesting. So what can happen is we can be given x as a function of a different variable and y as a function of that same different variable, and we have to find the derivative of them respectively. So what we can do is, if see it's as it is given here, if x is a function of f of t and y is a function of g of t, so what we can do is dy by dx would eventually look like dy by dt upon dx by dt. You guys understood this? This is something like very easy, and we can see a variety of applications of these in the future as well. So the differential coefficient using inverse trigonometric substitution. So sometimes the given function can be deducted with the help of inverse trigonometric functions and their substitutions, right? So this is something that also we can remember. For example, if we are given this, so this is very much equal to sine inverse of 2x root upon. Yeah, these are some formulas that we can simply learn and apply them while using our questions. So for example, if it had been given to us sine inverse of 2x into root of 1 minus x square, we can simply write it as 2 sine inverse x. Similarly for cos, similarly for tan, similarly for other functions as well. Okay. This is something that how can I like, if you guys want derivation of each of these formulas, you can simply put the formulas itself. But I would suggest you, of course, you should know the behind concept of it and know a bit of past of it. So I would suggest that you guys try and deriving these formulas by yourself, because this would give you practice as well, and deriving them would give you an idea that how a question works and how a formula comes about, right? So please try in doing that. Okay, so now what we have, these are other formulas that we have. This is the very known formula. This is nothing that is new to us. We had done this earlier, this as well. This is not something out of the box. Then we have logarithmic differentiation function. So if a function is a product and coefficient of functions such as this, we take the logarithmic and then switch it. Yes, this something we had also done in yesterday's class, that there were two functions that were being multiplied. So the first thing, and it was not easily solved applying the multiple product rule and the coefficient rule. So what we do is we take the log of it. So what does log do? Log conversion as summation and subtraction into division. So sorry, division into subtraction. So that makes our life very much easier. Okay, so now what we have here is differentiation of function with respect to another function. Okay, so if it is given to us that y is equals to f of x and g is equals to and z is equals to g of x, then difference to z is dy by dz is equal to dy by dx upon dz by dx. Again, it is very parametric kind of something that has been done here. Okay, so successive differentiation. If a function f of x is being differentiated with respect to x, then the result dy by dx or f dash x so obtained is a function of x, may be a constant. Hence, dy by dx can be again differentiated with respect to x. The differential coefficient dy by dx with respect to x is written as d square y upon dx square or f double dash x. Again, the differential term or coefficient of dy by d square y upon dx square with respect to dx is written as, okay, again, okay, these are telling how we define the differentiation and how does it look like. So it's very easy. We can write it as dy by dx square, d square y upon dx square. That means we have double derivated, or we can write it as f double dash x. Similarly, the other powers as well. Okay, so we have another theorem coming in, the Leibniz theorem. So if u and v are functions of x such that their derivative exists. Okay, so we'll get this part later on, and this as well. See, this is something that is a bit advanced for you right now. If you guys are not aware of the formulas and the equation that we did just above it, so I would suggest that you can see and go through these equations. But for my personal suggestion would be not to like look into these right now. If you specially find a question and you might see that these are somewhat related to the question that is being provided, then why not kindly apply the formula and move on? Because this is something that usually is not appeared in the question, but if it does, then why not? You can always be like more prepared, right? So why not? Okay, so back to our derivative or special type of functions. Again, this is more formula, so I don't think we have to learn this up. This is very easy. I'm not looking into it much. Okay, this is nice. So differentiation of a determinant is something that we can like work on. So what is given to us is y is a determinant of functions p, q, r, u, v, w, and l, m, n. So if we differentiate it with respect to x, so we have to differentiate each row, but one at a time and do. Okay, so differentiation of integrable functions. I didn't get what do you mean by that. Then there is partial differentiation. Partial differentiation, what do you mean by partial differentiation? So partial differentiation comes into play when the function is like a function is made of multiple variables. For example, f of x of t. So it means that f depends on are both a part of this function, and but we have to partially differentiate with respect to x. So what do we want to what do we mean by partial differentiation here is that we want to see the change in function only when x get changes and t remains as it is, right? So again, I'll repeat myself. The what do we mean by partial differentiation? We want to see the function change in function with respect to change in x, only keeping all the other variables constant. They are remain to be constant, only x changes. Okay, so seeing this again, what do we get the formula here as? This. This looks a bit complicated. So I'll get back to these questions again because partial differentiation has a very easy way of solving. So what we do is, for example, we have x cube t square and we have to partially differentiate it with respect to t x, only with respect to x. So f, sorry. So what we have is f is equals to this f del, sorry, del f of del x. This is the difference partial differentiation representation. So what we do, we take two t square as constant and we write is at 2x square. So what we have is 3x squared t square as our partial derivative. Let's move on. This is more kind of a theory lecture, I suppose, because yeah, you can see Euler's theorem. Here, Euler theorem states that if f of x and y be a homogeneous function in x and y of degree n, then x partial differentiation of x by del x plus y partial differentiation of y is equals to nf. Okay. So what do we mean? X del f by del x plus y del f by del y is equals to nf. So this is not that usable kind of an equation. You might find some uses there, but not always. Okay, let's move on to the second order derivative. This is something that is to be discussed. The first derivative is the slope of the tangent line to the function of the point. That is what we discussed earlier. Notion and formula we are aware of. Let's let's go to the second derivative of it. So what again we had defined what the second derivative looks like. Then what does the second derivative tell? Okay. Yeah, this is something very important that you have to remember. That if the second derivative is zero at a point, at any point the second derivative is zero, so what information do we get from it? We get no information about it. We cannot tell anything about the slope of f of x. We have no information. But if the second derivative of the function at any point is less than zero, then it means that it is concave down. Negative means concave down, positive means concave up. This is simply that you can easily learn and understand. Next, what we have is the point of inflection. Okay, this is very interesting that we can easily point of inflection mean when the graph changes its concavity. So what we mean by concavity, see usually a polynomial graph is somewhat made up of like this. It is of the pattern like this. So what we can see here is the concavity is changing here, right? It is a concave up here, this is a concave down here. It is a concave up here, it is a concave down here, it is a concave down here. So where the point where we can see a change in concavity is called the point of inflection. Okay. And at the point of inflection, what we have is the second derivative is okay. Just a minute. Okay. So what happens at point of inflection, the second derivative becomes zero. Again, I'll repeat myself. What is the point of inflection? The point of inflection is the point where we can see a shift or a change in the concavity of the graph. For example, if the graph was first initially concave up, then it goes concave down, then we can say that the concavity changed and there was a point of inflection. Next, second derivative test, sorry. So this is what we discussed earlier. What do we mean by this? This is very basic, guys. You must be remembering this. Okay, so this is something important. So I am not aware that like actually I'm not aware that you have covered you guys have done integration or not. But since we were talking about differentiation, integration, and substitution of functions, so a major part of substitution of trigonometric functions and their usage in the part of differentiation and integration is in lies while solving integration. So let's see that how many integrals are like how do we solve integrals by substitution of trigonometrical functions. Okay, so let's say we have to find the integral of this function dx by 1 upon x square. So let's not see the further steps. So what first thing that pops into our mind is that what we can do is we take 1 minus x square is equals to t. Okay, if we take it as t, so let's differentiate it. So minus 2t by x would be d. Okay, let's me write it. So if we take 1 minus x square is equals to t, and we have 1 minus x square is equals to t square. So minus 2x dx is equals to 2t dt, right? I'll cancel the 2's here. Then dx becomes t by x dt. Okay, then what is the value of x? The value of x is 1 minus x square is root. Again, so we are left with nothing here. If we do this, we get t dt by x, which is root upon 1 minus t square. And this is t. So t and t get cancelled and we're left with nothing. So it does not help us out, right? So the best way to go about solving this question is to use a substitution of trigonometric functions. So what we do here, we take t is equals to sine x. So dt becomes cos x dx. Okay. Then dx becomes dt by cos x into cos x. If you guys do not understand how did I get cos x, it's very simple. Okay, there has been a slight mistake. What we do is we put x is equals to sine t. See, that was the confusion here. So the x square becomes sine square t, dx becomes cos t dt. So how do we solve that? Cos t dt upon root over 1 minus sine square t. So this get cancelled. We get dt left. T and t is sine inverse 6. And the whole question becomes very easy for us. So some of you might question that why does trigonometric function substitution works? So the best way to understand is that the formulation of it, right? What does the formula of a trigonometric function look like? The properties and the identities, what do we have? The identities that we have is 1 minus x square t is equals to sine square t. So this equation is very famous. So whenever we find 1 minus x square, 1 minus y square, root over 1 minus t square, root over 1 minus plus t square, all these equations use trigonometric functions because we know that is always a trigonometric function that can be represented in this form. See, so we have a formula for 1 plus t square, tan square t is equal to 6 square t. So we have a substitution for here as well. That is why. So whenever we see 1 plus x square, 1 minus x square, we usually run towards the substitution part of it. So that is why the trigonometric functions and the substitution is very important. Now you have when you have an expression of form this, so what this is very simple. If we are having a variable or a constant in our equation, so we can use that variable by substituting as well. For example, if we a square minus x square, so what we do is we put as a square minus x square. So again, as I stated, okay. So anti-differentiation by substitution. This is something I don't think we have to cover this out. We'll leave this for the time being and see where the time leads us. If there's a time left, we'll probably cover this up. Okay, let's see one of the formulas here. I think we have time. So definition, indefinite integral. So if you guys know something about integrals can be of two types, definite and indefinite. By definite, what we mean is when the upper limit and the lower limit is defined. And by indefinite, what we mean is that the lower limit and the upper limit of differentiation integration is not defined. So again, if you're not aware about upper limit, lower limit, what I mean by these is at what interval do we have to integrate? See, what is basically integration? It is the graph sorry, it is the area covered by the graph over the x-axis. If I'm saying integrate this function, so I have to define a particular, if I'm defining a particular interval and I have to find the value of the integral here, so I have to find the lower limit and the upper limit, right? But in major cases, if I'm simply asking you an integration of a function without specifying its limits or the intervals, so what we do is we put the integrate the function by itself and put a constant c there, because we are not aware at what capacity the function might change. So we represent it by a constant c, and if the integrals are defined, so we get an idea about what our c could be. Right, so again, this is we'll just, yeah, this is basically scratching or starting with scratch of integration. So this is what we meant by a definite or indefinite integral. So this is the sign of integral, a sign of course you might be aware of. Then evaluating an indefinite integral. So these integrals that we have been discussing in the past were all indefinite because we were not defining an absolute interval while defining this question. So, and what somewhat you might be confused, like what does an absolute or a definite interval look like? So definite intervals look like 1 to 3, or 2 to 4, or 5 to 6, or 2 to 100, or 0 to infinity. This is a semi-definite, but then two works, for example. Okay, next, what we have is properties. Of course, we have some formulas of integrals. So what do we have here? K of f of x. So k is constant, so it moves out. See, constants are very easily solved while integration and differentiation because they have no role to play. They are simply put out of the function, and we focus our attention towards solving the function itself. Okay, so the next part of it, we have the integration of functions, trigonometric functions. So someone might would say that integration is the opposite of differentiation. That is, if you differentiate sin x, you get cos x. If you integrate cos x, you get sin x. And it is right, they are inverses of each other, but to a smaller extent. So let's do some questions. See, so these people have done some questions. So let's do some questions if possible. So we have to find the antiderivatives of each of the following. Like we find each of the following antiderivative in terms of x. Okay. So this was easy. This is also easy. Why not? Okay. So they are telling what the point they're trying to make is what you have to remember while solving these derivatives. So the thing that we remember is what is the thing that we're derivating it with respect to, or integrating it with respect to. So here, see this, someone would say this is similar, but this is not. Here the integration is done with respect to du here, but in the rest of the part, it's different term. Okay, so the next using substitution is also easy. It is given to us integrate sine of x into e to the power cos x dx. We do x cos x cos x st and minus sine x dx is dt. Okay, so what are we left? Minus e to the power dt with respect to dt. And what is that? Minus to the power d. Simple. Okay, so the next we have using substitution again. So this is also easy. What we can do here is we can take 5 plus 2x cube is equals to t, 3 6x square dt, sorry, dx is equals to dt. And we have a x squared term with our in the function, so we can simply write x by dx is equals to, sorry, x squared dx is equals to dt by 6. And we can write the complete equation now. What we have here with us is dt, this is in multiplication, right? So dt into root t integration. And what are we left with? T to the power half. So it is t to the power 3 by 2 upon 3 by 2. So 2t3 by 2 upon, and there is also a factor of 6 that we are missing out. That is also we has to be included. Next, using substitution. Okay. What substitution that we can take here is, yeah, the substitution that we have taken here is u is equal to sine 7x. This is very simple and very doable question. Okay, let's move on. So find the indefinite integrals. In each case, you can use the trigonometric identity to set up the substitution. Okay. So first question we already did very easily. Let's do the B part. The B part, what we have here is that integration of cot square 3x. We can write it as cos x square 3x minus 1. Then we can take cos x 3x. We can multiply it by 3 divided by 3. Then we can put 3x is equals to u, and then we can easily solve because this integration of cos x square u is known to us. A direct formula is known to us. So we can simply use that and get our final answer easily. Now, evaluating a definite integral by substitution. So, evaluating definite integral by substitution, 0 to pi by 3 tan x plus x square x. So, we can simply take here as tan x is equals to t, then we will be left with sec square x dx is equals to dt. And that makes our life very much easier and we can get the equation directly. Absolute value again. This is also very comparable. Let's move on. So let's do some questions. So these are the same PYQs that we did last time. But since it is a very similar topic, so I didn't find a different set of questions. So we'll try to do some questions again and see if we missed out some of these or not. Okay, this is a very nice question. I love, like, I'm quite a knack. I have a knack of these kind of questions. So let's try these out. What we have here is e to the power 4x plus e to the power 3x minus 4 e to the power 2x plus e to the power x plus 1 is equals to 0. Yes, if we take e to the power x is equals to t, so t4 plus t cube plus 4t square plus t plus 1 is equals to 0. Then if we divide it by t square, so what are we left with? T square plus t plus 4 plus 1 by t plus 1 by t square is equal to 0. So this, taking 2 out of this into this, would give me t plus 1 by t whole square plus t square plus 1 by t square whole square. But there is a minus sign here, there is a minus sign. So we can write minus sign here. No, this is wrong. So what do we have here? This is t plus, sorry, t minus t whole square plus root t minus 1 by root t whole square. This was easier, right? Okay, they have done something different here. Let's see what they have done. So what they're trying to do is they have taken t plus 1 by t is equals to y, and then they have solved the equations. So it is very easily solved here. So I've taken y square. Why have they taken y square? Because this would give them value of t square plus 1 by t square plus 2 is equals to minus 4. So there should be a minus 2 sign here. I don't know why they have not written a minus 2 here. But okay, there should be a minus 2 here. And why not minus? There should be minus 6. No, it should be minus 2 here. I don't know. There is something wrong with the question. It can be minus 2 plus 2 both rather. No one cares about it. Let's do some easier questions. So what we have is if x is equal to 3 tan t and y is equal to 3 sec t, then what is the value of dy square upon dx square at t is equal to pi by 4? It is very easy. First we'll calculate dy by dt, then dx by dt, then double derivative and simply get our answers out of it. Right? Next question. You can always pause the video and see for solution, guys, if there's any doubt. And you can search it as well. So the another thing that we had was f of x was equals to x cube plus x square f dash of 1 plus this. Then what is the value of f of 2? Okay. So let's see what we can do here. We can write f of 2 and try to see if we have a formula. So what does f of 2 look like? Mm, f of 2 looks like 2 cube plus 4f dash of 1 plus f double dash of 2 plus f. Okay, let's see what we can do here. So since we have a three derivative of the function, so let's assume it as a polynomial with the highest degree of 3. And on solving the double derivative, the single derivative, and the triple derivative, these are the children equations that we have. By children, I mean like the final equation that we have came up with, and we put it in the parent equation and then put the value of 2. Okay, so the next part. So if x ln into ln of x, the ln of ln x minus x square plus y square is equals to 4, where y is greater than 0, then what is dy by dx at x is equals to ln x is equals to e. So let's consider and differentiate it. So the differentiation what we have here is, so first of all we differentiated using the product rule. So this is what we have. And this the x minus x square plus y square becomes minus 2x plus 2y into dy by dx, and we all close the values. the constant values at zero, because the differentiation of constant values goes to zero. Okay, so now we take when x is equals to e, the root of 4 plus e square, and put the values of each of these in the like the equation that we had founded, and then calculate what does the final hero of the movie look like. Okay, so the next is for x greater than 1, if 2x to the power 2y is equals to 4e 2x minus 2y, then 1 plus ln of 2x squared divided by dx is equals to. And the answer is 1. And you can see what the solution look like. If we differentiate 2x to the power 2y, what we have here is 2y comes down, and we have, okay, so we have taken a log of these both equations, and then we have tried to find the differentiation of both of these. So let's differentiate. So what we have here is this. And this is understandable as well, I suppose. And then when we differentiate dy by dx, what we get is this thing as the complete function of x and n only. Next. This was a bonus question because I don't know why they must have committed a mistake here. Let's see this question. This question seems small and simple. What we have here is if f of 1 is equals to 1 and f dash of 1 is equals to 3, then the derivative of f of x of f of x plus f of x whole square at f is equals to 1. So let's do then differentiating both of the sides. What we get is this equation. This is an important equation. And when putting the value of x is equals to 1, we have f dash of f of 1, then f dash of f of 1, and f dash of 1, plus 2 of f of 1 and f dash of 1, which is equal to this. And the value get the what you get. Let's do this because why not? So e, okay. What is e to the power I plus x is equals to e. It is the next we're differentiating, right? F at dx plus y is equal to 0. Okay. So what do we have dy by dx as minus y e to the power y plus x. This is a plus sign, right? Yeah, this is a plus sign. Let's calculate dy square by dx square. So first, let's calculate what is the value of y at equals at x is equals to 0. So if x goes to 0, this is 0, this is 0. So e to the power of y is equal to 0. Never the case, because e to the power y is always positive. It would look something like this, right? Yes. So we do not have this set right. So let's put the value of at x is equals to 0 here. So at x is equals to 0, what we have here is this goes to 0, and we're left with minus of y upon ey. I think there is a mistake here. Okay. That was a mistake on my part. It is not e to the power y equals to 0. It is equals e to the power y is equals to e. So y becomes 1. So at x is equals to 0, we have y is equals to 1. How simple is that? 1. So dy by dx becomes minus of 1 by e. Now, if we further solve to calculate dy square upon dx square, we get the value answer. Right. Easy question, not something that can not be done easily. Let's move on to other question. Okay, so let's see another question. What we have here is that this question is easier. Let's do something that is not that easy for the time being. Do we have more questions, guys? No, we don't have more questions. So we'll see what we can do from these only. Okay, so what is given to us that x is equals to root of 2 cosec inverse t and y is equals to 2 to the power sec inverse t. Okay, so these now see I told you right, these require some formulas here, that what kind of differentiation cosec has and sec has. So let's see what are the formulas that we did earlier. Okay, I'll try to copy paste it for you guys, but it might be tough. Like this is simple, what we have seen in the differentiation solution also. It is just calculating and putting the value of inverse differentiation, right? Let's see where we did the, yeah, this is the part. No, no, not this. Okay, this is the key part. So differentiation of sec x is this, and the differentiation of cos x is this. This is something you have to remember and solve the equation that I had, that the question is being asked you to do. Let's scroll down and see if there's another question that does not require a direct formula and some logic. Am I able to scroll? I'm not able to scroll it down or what? I can. Okay, let's do this one. So what do we have? F of 3x is equals to f dash x into f double dash x. Then we have to find if any of these is true or not. So this is the polynomial based questions that can easily be done. I'm not doing this again. Is there something else that we can do? This question seems easy, but I have been covered with a page, so we'll not do this. Let's do this one. This is easy. Seems easier to me. 2x to the power 2y is equal to 4e to the power 2x minus 2y. So let's take log to make our lives easier. 2y log of 2x is equals to 2x minus 2y log of 4e. And this is nothing but, this is the constant value. Let this be a constant. So now let's start differentiating. So what we have here is log 2 dy by dx plus 2y plus 2 log x dy by dx. Okay. And then we have 2 minus 2 dy by dx into log 4. Right. So let's collect the dy by dx term. So dy by dx, we have 2 log 2 plus 2 log x, and we have plus of 4 log 4e, 2 log 4e. And then what do we have? We have minus 2y by dx and plus of 2 log 4e. Am I going in the right direction? I am actually. And then what are we supposed to do? We have to find log 2x. We are not having any log 2x here. Where is the log 2x? Okay, it's my bad, guys. What could have been done here? We could have omitted this step of expanding log 2x because the question itself was asking us a value to be contain having a value of log 2x. So let's not distribute it and solve it right now as it is. So 2y 2x dx won't come. So now we have this and a 2 would also come here. So it would be 2y to we have 2y by x plus 2 log 2x dy by dx is equals to log 4 as it is for e as it is 2 plus sorry 2 minus 2 dy by dx. Now if we select dy by dx term, so we'll get something out of it and you can see the solution as what the solution says as well. Where is the n term coming from? I'm not getting the n term. Achha, it's ln, sorry, my bad guys. It means ln here. So it's very easily done. They have simply taken out y terms together and put it in differentiation. It's very easy. I think we're done with for today's session. If you guys have any doubts and questions for me, please ping me in the comments. I'll try to solve those questions for you. So let's stop the class here. Let's move on to the next topics in future classes.